If you've ever sat in high school physics, you probably remember staring at a chalkboard covered in equations, feeling entirely detached from your actual life. When education relies strictly on rote memorization and abstract theory, a serious gap forms. Students learn to plug numbers into a formula to pass a test, but they struggle to apply that logic to solve problems in the real world. This educational disconnect was peaking at SMA Negeri 04, a senior high school in Bengkulu, Indonesia. This was the baseline data for the 10th grade class. When tested on their critical thinking skills, their ability to analyze and synthesize information, the students averaged a score of 34.24 out of 100. The standard textbook approach was failing to equip these students with the analytical skills they needed. To fix this, educators at the school replaced the textbook with a different kind of laboratory, a traditional dirt playground. They asked the students to play the traditional Indonesian game Lompek Kodok, which involves tossing a small marble, a gundu, toward a target box. This is the core of Ethno-STEM, the intentional practice of embedding rigorous science, technology, engineering, and math into local cultural heritage. Instead of reading about an abstract projectile on a chalkboard, the students use this traditional game to study the mechanics of motion and gravity. Local culture acts as a pedagogical Trojan horse, using familiar play to introduce high-level physics engagement. Every throw begins with a moment of preparation. A student winds up, grips the stone, and prepares to launch it. In the Ethno-STEM framework, this preparation is the ethno-engineering pillar. To win the game, the student has to make rapid engineering decisions, selecting a stone with the right density, adopting a stable stance, and estimating the exact force needed for the distance. The moment the stone leaves the hand, the Ethno-Science pillar takes over. Two measurable forces act on the stone simultaneously. The initial forward thrust provided by the student's arm competes against the constant downward pull of gravity. The interaction of these inputs forces the stone into a parabolic trajectory, transforming a game of chance into applied kinematics. To capture that motion in real time, the students carefully record the flight of the stone using a smartphone camera. This moves the lesson into ethnotechnology. The students import that footage into a software program called Tracker for frame-by-frame analysis. The software plots the exact X and Y coordinates of the stone as it travels across the screen, turning the physical throw into digital data. In the ethnomathematics phase, the students extract these digital coordinates to populate their project worksheets. Using the data they generated themselves, they calculate the precise initial velocity and the maximum height of the jump. By working with their own data, the students solve complex kinematic equations without relying on rote memorization. Back on the playground, the stone lands in the target box. Following the 5-meeting intervention using this project-based model, the researchers measured the classroom's growth. Student interest in physics rose to 87%. The impact on comprehension was even larger. The students' critical thinking scores climbed from the baseline of 34.24 to an average of 83.18. This improvement represents an end-gain score of 0.75, which places the class in the high performance category. This end-gain score points to a structural shift in critical thinking capability, representing a significant leap in how these students analyze and solve problems. These students are applying modern data analysis to traditional play, connecting ancient heritage with digital science. In this framework, digital technology and cultural practices act as partners to build a deeper understanding of physical phenomena. Ethno-STEM places the laws of the universe directly into the students' hands, proving that science exists wherever they choose to look.